Good morning, all of you. Today, I'll taking the seminar topic on review of additive manufacturing and 3D printing technology applied to multi-patient ventilator under the guidance of Dr. Ramya George, Associate Professor and Head of the Department, Electronics and Biomedical Engineering. These are my contents. Additive manufacturing is also known as 3D printing technology. It enhances the ventilator technology, material, multi-patient use. The seminar covers the evolution of additive manufacturing across different generations, highlighting the key advancement in methods and material characterization. The additive manufacturing methods are classified into generation-wise for the purpose of material application and technical, industrial, and mechanical field. Special focus on the design of production of ventilator components such as valves and actuators using AM technique called also, the innovative application of 3D printing for multi-patient ventilator using splitters, the innovation has expanded the comfort and performance of medical device for the specific solutions, highlighting the impact on the patient care and equipment manufacturing. The seminar focused on the additive manufacturing, different types of methods, and multiple patient usage. Additive manufacturing is a process where the materials are layered to create three-dimensional objects on the digital model. The technology has transformed various industries by enabling rapid prototyping, customization, and production of complex geometry that would be challenging or impossible to traditional manufacturing method. Through the 3D printing, we can rapidly produce essential ventilator components like valve, actuators, and connectors. This not only speed up production, produce, but also allows greater flexibility in design, functionality, and performance reliability. Moreover, one of the most advanced innovation in this field, ability to use single ventilator support multiple patients simultaneously. These are the literature survey. The journal paper is Additive Manufacturing Technology, Industrial and Medical Application. This paper is attempted towards highlighting the role of additive manufacturing. Also, this paper structured in the manner to focus on the various technologies and application of IAM, particularly medical field. The rapid design of ICU ventilator, the approach based on the smart switching and compressed air oxygen. The study employs utilizing the most commonly available ventilators, also deals with the valve and ventilator using manufacturing techniques. The next paper is the 3D printing omnidirectional soft actuators design, modeling, and characterization. This article presents the design and direct 3D printed novel omnidirectional soft pneumatic actuator using si- uh, stereolithography and elastic resin and fuse the poster model. The last paper is the simulated single ventilator dual patient ventilator strategy for acute respiratory distress syndrome during this COVID-19 pandemic. Demonstrate the ventilator in two patients is the one of ventilator with a mismatch and lung compressors is modified setup demonstrate that could be possible to achieve it using T-splitters. The objective of the seminar is three types: the evolutionary overview, generation-based classification, and second one is ventilator component design and innovation of multiple patient solutions. The evolutionary overview examine the evolution of additive manufacturing across different generations, focusing on the key advancement methods and material characterization. Generation-based classification analyze the additive manufacturing method by generation of their application and material, technical, industrial, and medical fields. Ventilator component like explore the design and production of ventilator components such as one actuator using additive manufacturing technique, innovation of multiple uses patient solution, highlighting the innovative use of 3D printing technology for multi-patient ventilator to the development of 3D testers. Advantage additive manufacturing. Additive manufacturing is a universal manufacturing technology, fabricating object by sequentially adding material layer by layer based on the digital design. Additive manufacturing enables the creation of complex structures mainly used in industries such as aerospace, automotive, healthcare, and offers beneficial like material efficiency, design flexibility, and reduce the production time. Additive manufacturing are technology classified into generation wise. The generation is also classified into method wise. And the first is stereolithography and selective laser sintering, electron beam welding, direct metal laser sintering, and direct energy deposition 4D printing methods. Next is need for additive manufacturing technology in this present condition. Customization and personalization. Additive manufacturing permitting the creation of customized product individual needs, which is beneficial in the medical application like patient-specific implants and multiple patient use. This personal prototype equipment likes and rapid prototyping and production. They introduce fast designing and prototyping, reducing the time of concept to production. The material efficiency and waste reduction. Additive manufacturing build object layer by layer, which is minimize the waste and making cost effective, maximizing the production and minimizing the waste. Next is 3D printing designing steps. The material selection. First, material selection. The materials are classified into solid, liquid, and powder materials. 3D model is CAD model, computer aided photograph made method, and Slicing this model is the machine is always a machine language. Computer is not machine language. So the STL file formation is slicing this model. Setting up the printer, setting a printer setup, the knob adjustment, and another part of setups. And printing is a process, and prototyping and pre-processing is the object developing, and final production is there is the post processing and quality control. Post processing is the sterilization and final surface finishing, and quality control includes the functional testing. The next is additive manufacturing methods. Additive manufacturing methods are classified into early stage, that first generation, second generation, third generation, fourth generation, and fifth generation. We can detailedly explain in the generation-wise methods. The first generation around 1980 to 1919 discovered in additive manufacturing technology. Methods are includes stereolithography, a method developed by Charles Scull in 1984 to 1986. This is used materials photopolymer, resin, and liquid form. High precision or high accurate value with a thickness ranging from 20 to 50 microns, fine edge and smooth surface. The technical equation is E is equal to IT. E is equal to exposure energy required the curved resin, and I is the intensity of light source, and E is the exposure time. This is the pictorial representation. This is the building block containing a liquid resin, and UV rays are solidifying the liquid film layer by layer. The product is produced. Next is fused deposition modeling. This method is developed by Scott Cram in 1988 and 1989. Used materials are thermoplastic like ABS, PLA, and PEEK. The average precision with the layer thickness range from 100 to 250 micron, leading to visible layer lines. R is equal to U into A. R is the rate of material deposition, and U is a nozzle speed, and A is a cross-section area. With a major area, prosthetic oath and deck delivery, scaffolding, and rapid cooling. The pictorial representation of the FDA FDM is, and the building material spool is like blue color, and supporting material in the red color. The nozzle is heated with above 100 degrees Celsius, and the spool is melted with the molten stage in 100 above 100 is, and layer by layer adding of the building block structure made up of the product. Next is selective laser sintering method developed by Carl Deckard in 1989 to 1919. This used materials like nylon, polystyrene, and some other metals. Average precision of layer thickness ranging from 100 to 150 microns, producing rough surfaces. The powder recycle capability is slower than FDM. The technical equations are E is equal to P into T. Energy required to sinter powder, and less P is a lesser power, and T is the exposure time. This is a method SLS process, and CO2 laser is used here. And the powder deposits the building chamber, and CO2 laser producing the laser power, and melted, and so melted with the layer by layering, and powders adding to the melted first layer, and layering of layer by layering adding of this powder, and CO2 laser melting, and layer by layering of the object produced it. And limitation. Limited photopolymer resin, which are brittle, not suitable for functional parts, more time required, and product of 3D printing process. Lower resolution and surface finishing is very complex, higher equipment cost, and mainly due to the use of laser powder handling systems. Next is second generation, around 2000 to 2010. The direct metal laser sintering is method introduced by early 2000. Those materials are titanium, aluminum, stainless steel, cobalt, chrome. The layer thickness ranging from 20 to 100 micron. The material efficiency is a minimal waste, accessing powder reuse. And technical equations are P is equal to E by A into U. P is a laser power, E is energy required for sintering, A is a cross-section area of the powder bed, and U is a scan speed. Next is this. This is the pictorial representation and processing of DMLS diagram. And CO2 laser is used here, and the building block is uh, the powder layer is deposited in the building block, and the CO2 laser is melted with layer by layer adding, and the powder is again repeating this process, adding of the powder, and CO2 laser power melting the powder, and object is developed. Next is electron beam melting. This method is introduced in 2009 to 2010. The used materials are metal such as titanium alloy, cobalt, chrome alloys, and layer thickness ranging from 50 to 100 micron. High material efficiency in minimal waste. Excess of powder can be reused. PC, the technical equations of PC equal to I into IR, electron beam power, and I is the current, and R is the resistance. And first of all, the CAD modeling, and second is slicing, and the R beam equipment is used here. The high energy of electron beam is solidifying the powder material, and layer by layer adding of the powder material. The electron beam highly affected, and the layer by layering of the product is produced. The limitations are limiting by certain metals and metal alloy, high equipment and operational costs, and require vacuum environment, making equipment expensive and complex. Surface finish is typically rough and may require post processing. Third generation is DET and LPBF, direct energy deposition. In this method, enacted by 2011, it is used to materials such as titanium, steel, nickel alloy, ceramic composite thickness layer ranging from 200 to 500 microns, high material efficiency and precision with minimal waste. And the technical equations are P is equal to E by T. P is the deposition power, E is the energy deposit, and T is the time. This is the pictorial representation. The two side of the dead process and powder is adding and the high laser beam is affected. Melt pool is formation is here and the layer by layer adding of the powder and the laser beam is melt with each of every powder and the layer by adding of this process is repeating and the product is formed. Next is laser powder bed fusion. This method is introduced by 2012. They used to material metals polymers. The layer thickness ranging from 20 to 100 micron. The high precision, excellent surface finishing with the minimal waste. The high material efficiency, unused power can be recycled. P is equal to E by A. P is a laser power, E is the energy input, A is an area. This early stage, it is the advanced method of selective laser sintering method. The limitations are limitation build size due to the power bed constraint, high equipment and material cost, increase the post processing time. Next is fourth generation 4D printing and multi-material 3D printing. The 4D printing introduced by 2021, multi-material 3D printing is in the 2022. It is used to material and metal smart materials. Smart materials are shape of memory alloy hydrogels, responsive polymers, and the changing shape over time or responsive to environmental stimuli like heat and moisture. The layer thickness ranging from to 20 to 100 microns and 10 to 15 respectively. The high precision and excellent surface finishing, efficient creating adaptive self-assembly, self-repairing structures, and creating embedded electron and sensors. T is equal to F of ST. T is a transformation rate and S is a similar ability like heat and moisture. T is a time. First of all, the CAD modeling is represented here. The printed materials like solid, liquid, and powder materials are here, and printed methods are FDM and selective laser sintering and stereolithography. And the final 4D printing, external stimulus like moisture and heat is applied here, and shape of the product is changed. The limitations are increasing the complexity of design and manufacturing process, and higher common multiple material usage in equipment. Next is fifth generation, fully integrated digital manufacturing. It is upcoming technology and at least innovation research taking field. AI integrated additive manufacturing technique used to material high strength and polymers, metal and ceramic, ensure high accuracy, real-time adaptive adjustments, maximize the material usage with no wastage. The production time is reduced to maximize the production and increases. And the technical equation O is equal to F of DMT as optimization function. D is a design parameters, M is a material opportunities, properties, and T is a process timing. And all the parameters are controlled by AI algorithm. Next is bioprinting tissue engineering. The materials used to biomaterials including hydrogens, living cells, and biolinks, cellular level precision for tissue scaffolding, organ printing and high precision of placing living cells with a layer thickness below 10 microns, high efficiency in creating complex tissue such as multiple cell type. Next is we can discuss about second focusing area of the seminar, the multiple patients using in ventilator, in same ventilator or single ventilator. When we can discuss about ventilator, what is ventilator? Ventilator is a critical care equipment and this is used in the critical care department. Medical device that help to patient breathe. It works delivering oxygen-rich air into lungs and removing the carbon dioxide from the body either to the mask or inserted to windpipe. The ventilator are critical care setting during the surgery or the case of respiratory failure. The device can be set of controlled breathing entirely depending on their needs. Then additive manufacturing process of valves in ventilators. The ventilator contains three types of valve, container valve, inspiratory valve, and expiratory valve. These booster methods are selective laser sintering and selective laser melting method. First is first is input requirement like solid, powder, and materials of the required to manufacturing valves. Next is designing phase stimulation and testing, material selection, biocompatibility and durability. Next is additive manufacturing process and post processing and quality assurance and final product assembly. The additive manufacturing process of actuators in ventilator. The two actuators are here: 3D printed soft pneumatic actuators and omnidirectional soft pneumatic actuators. The method are zero lithography technique. The input requirements and force and speed required to the powder and solid and liquid materials. Design phase and material selection, strength and biocompatibility checking, additive manufacturing process, layer thickness speed, and post processing, surface finishing and sterilization management, and assembly means motor and gear housing, quality assurance, functional testing, and final production making. And the characterization of ventilator equipment parts, customization, size and shape, lightweight design, and rapid prototyping, reliability and durability, safety, smooth and sand operation, vibration control. And next is corrosion resistance. Then we can move the ventilator using multiple patients. During the medical emergency, a single ventilator can support multiple patients using splitters. These standard splitters are used for patients in the same disease condition. To overcome this situation, we can use modified splitters. The modified splitters are controlled in pressure, flow, and volume, each patient with different conditions. This is a standard splitter diagram. The standard splitter developed in 2020. In 2019, novel coronavirus is widely spread in worldwide. In this, USA country is widely spread in, and the USA country has available of 1 lakh and 1,60,000 of ventilator required here. There is no chance of acquiring this ventilator, such as the Neyman and Babcock scientists are developed and develop a standard splitter concept and develop a standard splitter for the dual patient using a single ventilator. So the standard splitters only occur in same disease condition of each patient. So in USA widely debated this condition of this and disadvantages are occurred in the Society of Critical Care Medicine, and American Society of Respiratory Care, and American Society of Anesthesiologists, and Anesthesia Association of Respiratory Care, and American Association of Critical Care Nurse are widely debated the standard splitter disadvantages. The joint statement is prepared and 2020, and multiple problems are required. So the problems are, first is the inability to deliver different pressure to achieve required tidal volume in individual patients, and inability to manage positive and expiratory power like PEEP, which is critical important of these patients, and the risk of cross section, and this ethical issue, and the sudden cardiac arrest is occurred, and the difficulty to monitoring the both patients simultaneously. So the Neyman and Backup again rethink this standard splitter and develop a modified splitter with the inspiration is developed through another scientist, Palladino et al. The Palladino et al. Successfully completed the experiment. A 4 adult human-sized sheep is ventilated in 12 hours in a single ventilator. So this inspired the experiment. The Neyman and Backup scientists rethinked the standard splitter and developed a modified splitter. The modified splitter concept is this year. The standard splitter, the R is the all the resistors are represented the tubings of the ventilator, and the capacitor is represented here the diaphragm of the patient lungs. Next, the modified splitter also represent the resistors are represent the tubings of the ventilator. Also, the capacitors represent the diaphragm of the patient. The extra two resistors are here, RV1 and RV2. There are the controlling power of volume, flow, and modified splitters are used to uh, different patient and different patient condition and different patient diseases in one ventilator to control volume, pressure, and the etc. And the two diodes are placed here. Two diodes are control the backflow of mixing of inspiration expiration air in the ventilatory pipes. This is a 3D splitter diagram, and we can observation of this additive manufacturing and the multiple patient using a single ventilator. The additive manufacturing technology methods are demonstrate significant advantage, particularly in terms of customization, rapid prototyping, maximize material usage for the reduce the waste and cost efficiency. The 3D printing technology helps the multi-patient, particularly during the critical shortage of medical equipment and supplies. And 3D printing also allowed to rapid production components, particular parts and splitters, which can be enabled single when they can serve multiple patients simultaneously. 3D printing for multiple patients have observed a new possibilities and personalized medicine technology. It also presents challenges. And next is advantage and disadvantage. The advantage is customization and flexibility, rapid prototyping and production, reduce the waste, cost effectiveness, and enhance the patient care, and lightweight design is occurred. The disadvantages are material limitation and cost, production speed or high volume, cost of equipment, and limited functional testing. When we can conclude this seminar, the seminar aimed to develop a review of additive manufacturing and 3D printing technology applied to multi-patient ventilator, proper awareness of additive manufacturing method, reviewing additive manufacturing method, limitation, challenging and overcome the generation methods, and rapid manufacturing of material command, equipment, parts, single ventilator using multiple patients in critical emergencies in like novel coronavirus or COVID-19 occurred, and 3D printing enabled the creation of lightweight design in present challenging phase through traditional method, enhancing the efficiency and performance of multi-patient ventilator in the ventilator system. The scope for future work, integration of smart technologies, advanced material development of maximum usage, sustainable manufacturing practice, and personalized medicine applications. These are the references to help me to making this PPT and the report making. Thank you.